pleasure to introduce to you today Dr. Susan Bird. Susan Bird was graduating in 2008 from Northeastern University, and then she did a 4-year postdoc at Brigham Women's Hospital in Boston with Bruce Crystal. Bruce Crystal is most known, I guess, for his electrochemistry work. Super sensitive analyses of metabolites over the years, and very meticulous also thinking about quality controls and setting up designs and looking at study biases. So that's how I came to know him. So she said that at that time she set up metabolomics, lipidomics, especially lipidomics, in Bruce Crystal's lab. And then she went in 2013 to Thermo Fisher, where she went through many different core labs and many different other labs in terms of understanding their needs. So she got a really good overview about application areas, and especially in the Boston area, which is a very hot area in science in general, but also in metabolomics and lipidomics. When you just look at the job advertisements per month almost. And 2 years ago, I think. Last year. Okay.
A year last week.
She took over the role in vertical marketing metabolomics. I just read that from here. With the idea to kind of empower research globally in metabolomics and lipidomics, because that is a growing field, including at Thermo Fisher. We just talked about like some trends yesterday evening. The trend is clear. We're on a winning streak. Okay, it's not clear to everybody yet, but that's why Susan is here to showcase what Thermo Fisher is bringing to the table, to learn from us, and to get into a fruitful conversation. So she is totally open for us to do the regular thing, meaning asking questions as they arise. You don't have to be shy. This is really like a normal seminar where we can say, well, that graph, I don't understand the axis, can you explain, or whatever, right? So that's okay. With that, Susan, the floor is yours.
Perfect. Thank you, Oliver. Thank you, everyone. And for the last 2 days that we have been here, I think we've had a lot of great discussions. I've gotten to know a lot of you. I appreciate everyone coming to hear what we're going to talk about today. So you can see our vision. I titled this talk, Metabolomics Squad Goals, Orbitrap Workflows to Empower Your Research. You see SQUAD is all in capitals. It's an acronym that I'm going to define for you throughout this talk so you can understand what SQUAD means, how we're implementing it, and how you can try and implement it as well in your research. So what are we going to discuss today? First, I'm going to introduce the team. Oliver gave a nice introduction, vertical marketing, kind of what I do. I'll give you a little bit more information, what we do. You'll run into other vertical marketing teams at Thermo, and now you'll have a little bit more understanding of kind of who we are, what we focus on, and what we're trying to do. I'll give you an introduction to SQUAD using our Orbitrap Explorers 240, some applications on it. Switch over to our tribrid instrumentation, specifically the Orbitrap IQX, which is small molecule specific tribrid. Show you a little teaser of SQUAD on a tribrid, and then give you a little bit more information on that instrument and how it could impact metabolomics and lipidomics research. So let's talk about the team. You'll see there are 3 of us here today. I am the leader of the team. By no means that means that I know more than the 2 guys on my team who know everything, and I just kind of parrot what they do. But what our job is to really build workflows and understand what the market needs, try and see where people are struggling, and help build solutions within Thermo to kind of reduce these struggles, hit your pain points, right? And this is everything. I know we focus on mass spectrometry. Clearly, we all love it, but it is everything from design of experiment all the way through to data processing and reporting, right? We cover every part of the workflow, and our interests and our skills between the three of us are in kind of overlapping areas. So it's good to have different viewpoints on what we can do. So Bashar and Rahul are in the audience. I definitely invite you to talk to them afterwards on kind of what their research is and what they're working on now. I'll indicate on our slides who did what and kind of where we're going in the future. So what are we doing and why are we doing it? I think everyone in this room definitely understands, you know, omics insights into biology and why we are trying to study all of these areas, right? If we are just focused on genomics, we are missing a lot of what is happening in our RNA proteins, and then especially metabolomics and lipidomics. This is where we sit. This is telling you really what is the phenotype, what is happening in the cell, in the body, right, with including microbiome and environmental interactions. So how are we at Thermo Fisher working on this? And we are addressing all workflows in our team. We're going to start with looking at untargeted discovery workflows, where really we understand that researchers are trying to get an ultimate coverage, and you are looking at breadth of analytes and number of pathways coverage. You really want to see as much as you can see, because your hypothesis isn't fully defined yet. We also are working on targeted quantitation studies, right, where you need ultimate sensitivity. You do have a well-defined hypothesis. You want to see what these molecules of interest are doing, how they are changing in your study. And then finally, I said I would define squad. We are working to really implement this together in a simultaneous quantitation and discovery assay. That's so that you could get the most out of a single injection and get most biological insights into your research. And we do have some examples on how we've implemented this. So here's what we are working with at Thermo in terms of analytical solutions tailored for metabolomics and lipidomics. I just want to draw your attention that we are focusing today on LCMS techniques, but we also can incorporate IC and GC and connect them to our mass spectrometers. We know that the metabolome is diverse. You need different types of separation in order to get a full comprehensive picture. And at Thermo, we're well positioned to do that. In addition, we support everything from triple quads, our Orbitrap Explorers, benchtop Orbitraps, as well as our Trigrid series. And we have a suite of software that can help you on each of these instruments. Today, in the beginning here, I'm going to start by talking about our Orbitrap Explorers benchtop system and how we've used that to establish squad analysis and how we are moving forward. So let's consider those major workflows that we talked about: discovery, metabolomics, and lipidomics, right? Or an untargeted assay. Really, what are you doing when you kind of embark on this research is that you are taking into account everything that you are acquiring from your sample. You aren't limiting what you are looking for. And here you get a lot of peaks. And primarily at the end of the day, you're going to ask yourself kind of, what are all of these peaks? And then when you're doing a targeted analysis, as we just discussed, you're looking at these same areas of importance. You're taking into account sample prep, biological interpretation. You're leading with your hypothesis. You have a generated target list. You know what these compounds are, what they look like, and then you're getting a very specific data analysis and quality of analysis. But we know that there are compromises to both of these types of workflows. And what are you compromising here is that in untargeted, you're lacking quantitative accuracy in terms of utilizing concentration, right? On Orbitrap, it's a very quantitative instrument. I don't want to have it sound like it isn't, but you are complicating your data processing, and really you're looking for everything, right? So you're setting yourself up for having a very hard time getting through your data. With targeted hypothesis-driven workflows, your compromise is that you're biased towards these biological targets of interest, and you're omitting potential metabolites of importance. Untargeted analysis, as we all know, you could always go back and look for something else. Someone asks you, can you see this? You could go and retromine your data. A lot of times in targeted, you don't have that option. And so we are working to try and get you everything, right? So for squad analysis, simultaneous quantitation and discovery, what we are implementing at Thermo is allowing you to really start with a very efficient design of experiment, have the targets in mind that you think are going to be of importance, and you build that into your sample prep, right? So we are incorporating stable isotope labels into our sample prep to emphasize confident identification during the analysis, also get you absolute quantitation and do instrument and method validation. So we know in metabolomics and lipidomics, there are very large studies. Oliver, your lab has some of the largest studies that I see, right? Thousands and thousands of samples that come through. There's so much that goes into making that work, and standards assist in all of this. So for your data analysis in a single injection, and I'll show you a little bit more about how we do this on the Explorers, you are capturing both your targeted and untargeted data, right? We're using full scan. Orbitraps are great. You have very high resolution, right? And very accurate mass. And this comes into play on why it's important to have those kind of figures of merit when embarking on squad analysis and how they impact the results. And then we have two different sets of data processing software that kind of help you get through it all, right? You're still generating lots of data. You still have a little bit of a complication in terms of understanding what everything is and what it all means, but we do have software in place to kind of assist you in that undertaking. So let's talk briefly about the Orbitrap Explorers 240 mass spectrometer. It's a benchtop system, quadruple Orbitrap. You can do MS-MS fragmentation on it. You can see on this slide, it operates in 3 modes. We're talking about small molecule analysis, and anything that you see in red here on this slide is a benefit towards small molecule analysis. So it has a very low mass range, goes down to 40 m/z. You have a maximum resolution on this system of 240K. You can incorporate easy IC. So on Orbitraps, our standard specs are that you can achieve 3 part per million mass accuracy when it is external calibration. With internal calibration, you're achieving sub ppm mass accuracy. That really helps when you're trying to identify unknowns and reduce your data. So your untargeted analysis, I said you're going to be looking at this and saying, what are all of these peaks? The more accurate your measurement, the more you can reduce your data and get a smaller list of potential hits. Polarity switching, that's very important. I have a little metric here, but I'm going to show you in terms of data what it means to use the polarity switching on the Explorers and how that can increase your throughput and get more out of a single injection. And then finally, we have AcquireX, which is our iterative exclusion list generating intelligent acquisition software. It's great. It's on the Explorer series instrument. It's on our tribrid. It will help you dig deeper into your sample and get more MS2s and more useful MS2s, not just more MS2s, I should say. So why, again, is it important to have a high resolution and accurate mass when we are embarking on these studies, right? Here's an example where we are just trying to look at different resolutions available and trying to separate out isomers. We have these two these 2 phospholipid species. We need to be able to get to 60K baseline separation in order to do in order to get good resolution for accurate identification and accurate quantitation on these species. This is achievable on the Orbitrap Explorers system. In addition, we want to be able to separate out the isotopologs so we can start to identify species that we don't know. And this is, you get the most out of the higher resolution. So here you can see that we could get fine isotope pattern, really pull out what the sulfur 33 and nitrogen are in that A1 peak when you are using an Orbitrap. And then finally, what does this all mean at the end of the day? When you are trying to reduce your data, get annotation specificity, the more that you can restrict your limits when you are searching, when you can say, I know that I have sub ppm mass accuracy, I can restrict my searches to at least 3 parts per million, or, oh, sorry, a little quick there. You can restrict down to at least 3 parts per million, you are reducing your potential hits. And then with the fine isotope resolution, you can further restrict what the potential unknowns are. So these are benefits when you are embarking on untargeted analysis, targeted analysis, as well as doing squad. So let's talk about application of squad on the Orbitrap Explorers 240. All of this work was done by Bashar. So any specific questions, we're gonna direct them to Bashar. But what we did for this analysis was really to test kind of what was doing untargeted and targeted metabolomics on milk samples. So Bashar did a simple sample preparation where he also included isotope labeled, spiking in isotopically labeled amino acid standards, looking at different types of milk, different types of cow's milk, different type of fat concentrations, organic, non-organic, and also incorporating plant-based milks into it to see what the metabolomics is on these samples. We use the Orbitrap Explorers 240 for all of our profiling. We did profiling full scan, 120K, positive and negative switching in a single injection. So all of our profiling experiments were single injection, and we did our targeted analysis using Trace Finder based on those amino acid isotopically labeled standards. All of our untargeted analysis was using Compound Discover. And I'll talk about that in a little bit, what these data processing software platforms are like. So what goes into the experimental setup and design of experiments? We all know you have to incorporate QCs. We use pooled samples. I know you use pooled samples as well. So understanding how to properly include standards into your sample prep and into your QCs, randomizing the order of sample preparation and injection to take out any variations that are due to the analytical system. And then these internal standards you'll see are going to be used for quantitation and for looking at system progression of the system over time. And what I mean by that is that we are going to be looking at two internal standards that were included to be looking at the robustness of the system. Are we maintaining mass accuracy? Looking at our QC samples. This is how we determine, I know we only did 40 samples. You guys are doing upwards of like 20,000 samples. When you incorporate these appropriate QA and QC methods into your analysis, you know that you have high quality data coming out at the back end. So much of metabolomics is unknown that you don't want the unknown part to be variations in your analytical technique, right? And so really kind of starting up front and making sure that you attack that gets you high quality data on the back end. When we were setting up kind of the squad study in order of injections, you can see that because we were incorporating stable isotope labels and doing quantitation, we included 2 calibration curves into the injection time frame. All of these are doing just MS1 only, positive negative switching, and then you can see we have AcquireX deep scan on these pool samples, doing positive and negative modes separately when you're doing AcquireX. That's how you get really deep into the metabolome, and you can start to see compounds that are lower intensity. So we talked about positive negative switching. Let's look at the figures of merit on that. We know that you want to have at least 8 points across your peak in order to get accurate quantitation. I said that we were doing positive negative switching here at 120K based on phenylalanine and uric acid in these samples. We know that we are getting 8 points at 120K. We check on all of these aspects incorporated into our chromatography, maximizing how fast we could go with retaining data fidelity, right? And so this on the Orbitrap Explorers, if you subscribe to 10 points across the peak, you could do it at 60K. If you want 8 in this method, you could do it at 120. So let's talk about AcquireX. AcquireX was launched, I can't even remember now, I'm gonna go with 2018, as an intelligent data acquisition software that helps you get more meaningful data, not just more MS2s, right? This is really what we need in metabolomics and lipidomics. We have all these species, we don't know what the heck they are. We need to fragment them to figure it out, right? AcquireX facilitates in that by helping you through software in the instrument generate iterative inclusion and exclusion lists on the fly. So when you run an AcquireX experiment, we run it on our pool sample on our QCs. You can get then an understanding of every compound in your study. You start off by running a blank, and you use that blank to provide an exclusion list on the fly. So you inject a blank, you get a peak list generated from the instrument, and that is your exclusion list. You see you're taking out your background ions. Then you inject your sample. When you inject your sample, what you are doing is incorporating an inclusion list. You are injecting and just doing full scan on your sample and generating an inclusion list based on whatever thresholding that you incorporate. You can then use this to identify and eliminate if you want to focus on your protonated species, and you can remove any of your adducts or otherwise that are in the sample. That's an option for you when you are using AcquireX. Now you start injecting your sample and doing data-dependent MS2. So you can see here that we are looking at typical thresholding of your more intense ions. This is your first injection. Everything that was labeled there, 1, 2, and 3, are now going to populate automatically onto your exclusion list. So your inclusion list and exclusion list are always changing with each injection. Exclusion list is growing, inclusion list is decreasing. With each subsequent injection, you're getting further into the metabolome. You can see that we can now get MS on these lower abundant species. And what does that translate to? So we know that if you are to inject data dependent several times in a row, you are going to get a little bit of increase in differences on MS2 coverage just based on what is happening during the LC, right? When you're using AcquireX, you are going from approximately 40% coverage in MS2s up to maybe this is around like 82% by using AcquireX, and this is only 3 injections. So we know that these are multiple injections, right? However, those multiple injections are then able to be incorporated into Compound Discover for data processing and map back to your samples. There's another visualization of this. You can identify that in AcquireX, you can see that traditional data dependent, you have this threshold here and you are not getting fragmentation on any species below that. By using AcquireX, you are getting much more fuller coverage of MS2. And then what this meant in our milk samples is that we were getting around 84% MS2 coverage of all of our MS1 compounds based on Compound Discoverer and how we label compounds, right? So that's removing background ions, that's removing redundancy in adducts and other species that you can eliminate from Compound Discoverer. So we're getting you all of this data, right? I identified that we have lots of software in place to kind of not leave you hanging on that. We're going to help you process and get to some answers quickly. So these are a suite of tools I just want everyone to be familiar with that we have to help you. Compound Discoverer is what we use for differential analysis and all types of metabolomics and lipidomics analysis. MZ Cloud is our own spectral library that is open. You can search it at any time. Tracefinder for targeted analysis. MZ Vault is how you can build your own spectral library. It's incorporated into Compound Discoverer as well, and also includes retention time then in your library. Lipid search for lipid identification. Mass Frontier, which I will talk about later in the talk for some different experiments. Mass Frontier is a piece of software that I think is underutilized in the power that it has to help you identify and annotate unknowns in your sample based on putative IDs. You can look in Mass Frontier and say, this is what I think it is, and it will help you really cover the compound and the fragmentation spectra and help you build up these compounds based on structural similarities. And we just went over AcquireX, intelligent instrument control software. So briefly to go over Compound Discoverer and what you get, it's end-to-end capabilities for what you need in one package, everything from retention time and alignment all the way to pathway analysis and statistics. So we are getting you everything from aligning your chromatograms, what are all of these peaks in these chromatograms, to helping you visualize the data in different ways that make sense to you. I think I have some. This is on our MZ Cloud database. What's important here is that it's a highly professionally curated database. Each spectrum that is in there is manually annotated, and we are looking at spectra from different instruments, different energies, and also MSN trees. So it's not just the number of compounds that are incorporated into here. You could see there are greater than 21,000, but within that, there are greater than 10 million spectra. So you can search based on how you are acquiring your data. Different fragmentation energies generate different fragmentation spectra. Incorporating MZ Cloud into CD allows you to really start getting more information from your data faster. This is looking when we have an MZ Cloud hit. There are also ways to incorporate MZ logic, which is an algorithm in MZ Cloud when you do not have a direct MZ Cloud hit. You can use other databases such as ChemSpider to use the proposed structures and then search MZ Cloud for substructure hits. And then that will give you a logic score to say, we know that this isn't a good hit, but this could potentially be similarities in your compound. So it's getting you closer to identifications of those true unknown species. And then finally, molecular networking to see what's related in your sample. This will help to understand biological significance, but also some of these species, the different colors indicate whether or not something is identified. And then you have the bars that are linking them. So you can start to see substructure similarities as well, these graphs. So let's go back to what we started with here. We are looking at squad analysis on our 240, looking at metabolomics in milk. So what did Bashar find out when he did this? So first we were talking about quantitative accuracy. And here you can see by using full scan, we are able to get 5 orders of magnitude quantitation, linear dynamic range of the amino acids that were spiked into milk samples. And from this start of the hypothesis driven, right, we're looking at amino acids. We can see that there are some differences here. If you look at phenylalanine between organic and inorganic milk, and then between the different fat contents. But you look at this and it's nothing like, it's not earth shattering. And also I don't know what this means in terms of milk. It's not kind of what my skill set is, but we also want to see everything else that's in that sample. So by doing untargeted analysis at the same time, not limiting our study, we were also able to identify certain organic acids that were also differentiating these species in cow's milk. So we aren't limiting anymore based on our hypothesis. We are getting more information from that single injection. And then again, we looked at cow's milk versus plant-based milk. This has a little bit more differentiation for you based on the amino acids and being able to identify differences in these milks. And when we look at the untargeted analysis, we can see some great differences, several-fold based off of these species here. So there is a significant importance on incorporating both types of analysis in a single injection and making it easier to achieve. So just to kind of recap on squad analysis, our positioning for this is really, it's to help you get more out of a single injection, right? So you can determine your specific research questions without compromise. You can maximize sensitivity of this method. We looked at everything in full scan. You can do PRMs. You know that when you're doing that, you are then compromising your untargeted analysis, but that might not matter to you, right? Incorporating labeled standards for QA and QC and utilizing AcquireX for deep annotation. And then you could go here to read more on kind of the history of squad analysis. We've identified a name for this analysis. Historically, it was called many different things, semi-targeted hybrid analysis, targeted, untargeted. None of these names really kind of captured what the type of analysis is getting you. So we went and kind of put our kind of stick in the sand there and naming it simultaneous quantitation and discovery, or SQUAD. So please, I encourage you to read this very comprehensive review. So going back to kind of all of our solutions that we have tailored for your metabolomics and lipidomics, we just were focused on the Orbitrap Explorers platform for SQUAD. Now we're going to talk a little bit more about tribrids. You could see here, tribrids are really best positioned when you want to get more confirmation and structural confirmation of your compounds. So in an Orbitrap tribrid, here is the schematic for an IQX. I will walk through this a little bit. We talked about an Explorers, which is a quadruple Orbitrap benchtop system. On our tribrid, specifically here is an IQX. In addition to the quadruple and in the Orbitrap, you have an ion trap on the back end. So it's called a tribrid because there are 3 mass analyzers: quadruple Orbitrap, ion trap, 2 detectors, Orbitrap and ion trap. So now you have two detectors at your disposal. You can really parallelize what you are doing. You can truly do simultaneous quantitation and discovery if you are able to indicate where you are moving your ions. Some unique benefits of the IQX is that you have different types of fragmentation modes as well. HCD fragmentation is what we're using on the Exploris. On the IQX, you have HCD and CID, and then MS to the N fragmentation. This gets you more information for those true unknown identifications. We also have UVPD. I won't talk about this today, but we have a great set of experiments that we did in collaboration with Oliver's lab to try and utilize UVPD for lipid identification. I wish I had it on the slide. We also have a talk at ASMS from Rahul on that work. It's really cool. Like Oliver said, my background is in lipidomics, so I really feel strongly about how cool it is that you can now start to not just get maybe this is a lipid with these fatty acids. We can really start to tell you, no, this is what it is. This is what it looks like. This is SM1 and SM2 position. This is where your double bonds are. It's some really amazing work. And then you have, I apologize there, 1M on this system as well. So why are multiple fragmentation modes important? And here's just an example of looking at the same compound, succinic acid, in both HCD and CID. And you can see that if you're just using HCD, you are not getting full fidelity of fragmentation of this in negative ion mode. Using CID, just for MSMS, you are really getting beautiful fragmentation to try and identify the species. So you're getting improved characterization and annotation. And in addition, if we are going to be doing any targeted PRM on this, CID is going to be the way to go, right? We're going to get more sensitivity when doing that analysis. So what are the squad considerations on a tribrid? And this is work that we did in collaboration with Oliver's lab. This is, you can see Elise and Oliver there, incorporated them up there, because really we wanted to see, all right, we have these two detectors, how are we going to use them, right? And it's not as straightforward as just kind of saying you're going to use the Orbitrap or the ion trap. What Elise did very thoroughly, I would say, and this is just a teaser for you. She also is going to have a talk at ASMS, which is going to be much more thorough than what I'm giving here. But we have these different mass analyzers, right? We have an area where we're going to do fragmentation. Elise was able to very systematically understand where it was most optimal for her targets, which were very low level, to do isolation of these targets, either in the ion trap and detection in the Orbitrap or in the ion trap. What we want to do is exploit the instrument duty cycle, sensitivity, and dynamic range for her targets while maintaining the untargeted portion of her analysis. She also assessed whether you are going to be doing isolation in the quadrupole with fragmentation and detection either in the Orbitrap or in the ion trap. So there are many iterations here. As we just saw with succinic acid, it's going to be different for each compound. So there are considerations to take into account when building this method. However, from the work Elise did, we were able to build instrument control software, I forget what they're called, but instrument control software templates that are able to get you a little bit further into building these methods on your own on the IQX. So this is all I have from Elise's data, but she will share a little bit more, right? I'm not gonna steal your thunder on that, Elise. I'll just say it turned out really well. We're very proud of that work. We're proud of what Elise was able to accomplish, and we hope to work more on this. Bashar was able to utilize squad analysis looking at SRM 1950, spiking in our favorite amino acids, right? This is on the Orbitrap Ascend tribrid. It's different than the IQX. I will very briefly just identify the areas of difference. So we have two ion routing multipoles in this system, which means that we can parallelize our ions a little bit more effectively. You can use the two detectors in parallel more effectively, right? So that is what you are getting from the Orbitrap Ascend. For all intents and purposes, the rest of it is the same as an IQX. And what Bashar was able to do was incorporate targeted quantitation in the ion trap. And by doing so, he's extending the linear dynamic range of his targets. Here we are seeing phenylalanine with the LOQ of 5 pentamol on column and 6 orders of magnitude. If I were to show you what we were able to achieve doing full scan Orbitrap detection, This is an LOQ of 50 femtomol on column and 5 orders of magnitude. I mean, they're both really great, right? But you can get the additional sensitivity you need by using the ion trap. And then you're also not, by using the ion trap and PRM, I should say, but then you're also not compromising your untargeted analysis by doing so and doing all of the untargeted in the Orbitrap at the same time.
So, do you have any idea how the sensitivity might be different for different molecules? So phenylalanine is a nice one. You know, it's aromatic, it's accepting protons and whatnot, it's fine. But what about like oxylipins or really more difficult ones where you actually need to look at really low concentrations?
Right. So then I don't know. Right here, all I want you to compare is that full scan Orbitrap quantitation versus ion trap quantitation in PRM. That's the only comparison I can make here. But for those lower level species, some of which I know that Elise looked at, by doing PRM and ion trap detection, she's getting more sensitivity there as well than doing full scan analysis. So from what I understand, Elise, in the previews I saw, doing untargeted, she cannot see some of these low level oxylipids. By targeting it in the ion trap, not only are you seeing them, you're quantitating them, and you're not compromising the rest of your untargeted. But it's a good question. I never know how to answer that. I can only answer it right now for phenylalanine. Any other questions? So we're going to move away from squad, but I want you to remember it and ask Oliver to run it all the time. Got it? When you go to URI, say, I want to run squad. That is what you have to do. So we're going to diverge a little bit here. I'm going to talk a little bit more about the IQX. One area that I did not introduce on our IQX is that there's an aspect in here called real-time library search. And I'm going to introduce you to that a little bit further, but real-time library search is only available on the IQX and Eclipse and Ascend mass spectrometers in our portfolio. So why are we using real-time library search and what is it? Here's the challenge that this is all work done by Rahul. This is a challenge that we have the identification of unknown metabolites, degradants, or transformation products that share a substructure and need more than MS-MS fragmentation in order to truly identify them. And for that, it becomes difficult. Like, how are you going to incorporate generating this MS to the third fragmentation just by doing data dependent? You're really wasting a lot of your time doing that. How can we do it more efficiently and get you to the answers that you need? So here we did this by incorporating real-time library search. So I will go over what this is. The step one is creating your own compound database. You have to have a library to refer to, right? So we have a library builder method template in our system that allows you to look at different type of fragmentation energies and different type of fragmentation mechanisms. So you can build up a pretty comprehensive library. Here we're just showing HCD and CID. Rahul also did UVPD for this analysis. So you're building your library, you can see, and then curating it using MZ Vault software, which I introduced earlier as part of Compound Discover. Now you have your library. And what does it mean when you're doing real-time library search? This is a snippet of what the instrument control software will look like. You can see that this is primarily your data-dependent MS2 with this extra section here. After data-dependent MS2, for every fragmentation, you're going to match against the library that you just curated. When you have a match, then you're going to say, okay, let's do MS to the third on it. No match, continue running your data dependent, right? So this is targeted towards your species of interest to get more informative fragmentation. Again, utilizing both those detectors. If you have a tribrid, use them both, right? You have them. Let's use them more intelligently as well, and then get more structural annotations. So what does this look like in practice? Here is your first injection. You're doing full scan, experimental MS2. You're matched against the library. Fantastic. Now we have a similarity match. You can incorporate, you can then have MS to the third triggered in two ways. You can either trigger on these unique ions, or you can trigger based off of intensity. I think it would matter. You would do this depending on what you're finding to be most informative for your species of interest. and then get an MS to the third. So how did Rahul test this? He looked at flavonoids, knowing that they have sharing a core structure here, which you see is bolded as structural similarity, and then having other areas that we know when you're fragmenting this flavonoid, you're probably not going to get informative MS-MS fragmentation to help you identify these species. So there was a standard mix here. We did this in collaboration with Metasci, and using the standard mix, that is how he was able to generate his library. And then what did the data look like? You can see here that we are getting more putative flavonoid identifications with MS3 in real-time library search versus no real-time library search. So we're getting more MS3s, right? That kind of makes sense. However, we know that for the increase in what is triggered, we know that these are being triggered on flavonoid compounds. So if you're just doing data-dependent MS3, you're just basing it off of threshold. It could be anything. Here, we know that we are targeting what we are trying to target. And what does that relate to? Here, you can see I talked about mass frontier. That is how Rahul was able to process all of this data. He had a putative ID for gallocatechin, was then able to use mass frontier to annotate this MS to the third, triggered only in real-time library search. It was not triggered in data-dependent MS3 due to intensity thresholding. So we were able to dig deeper, like with AcquireX, you dig deeper into what you are looking for. And here we could just talk about utilizing the multiple detectors on the tribrid and what real-time library search gets you. So if you just look at these bar graphs, you have MS1, MS2 triggers and MS3 triggers, no real-time library search and real-time library search. You can see the difference here with real-time, without real-time library search, you definitely get more MS3s triggered. But do you care, right? In this experiment, we want MS to the third triggered on flavonoid compounds. So we don't really care that we have a compromise here because we know that these triggers are important to our analysis. And by doing it in this way, we get more MS2 triggers on the other stuff that's there. So again, this is a type of squad analysis. You want to get most out of your single injection. Here we are targeting flavonoids and trying to identify them all. In addition, maintaining data fidelity on everything else that is in there. And here's an example. He was able to pull out that we were able to identify adenosine in these T samples, in addition to looking at all the flavonoid compounds. So that is all that I have to show you guys today. I'm not sure where I am on time, Arpana, if I'm early or late, or if it's good, but let's go over what did we discuss. Again, like I said, all of this data was done by our team, and I'm very grateful that I can present it to you. So we talked about squad analysis on the 240, getting the most out of a single injection, really considering your design of experiments, understanding how you are going to prioritize your quantitation, then looked at that in milk. All of this work, again, was done by Bashar. Gave you a little teaser of squad on a tribrid, work developed by Elise in collaboration with our teams in San Jose. Also, introduction to the IQX and flavonoid analysis, doing real-time library search, which was all done by Rahul. And thank you.
Thank you, Susan. Thanks, Rahul Bashar, for this excellent work and innovation, really, in metabolomics, data acquisitions, and data analysis. I think, Thermo Fisher has solidly placed themselves in front of the developments, which is excellent to see in the landscape of industry. So are there questions online already?
There are questions online. I'll start with the squad questions. So the first one is, with Orbitrap's slower scan rate and then adding polarity switching on top of that, how does that impact quantification on both high and low abundant compounds in a complex sample?
Yeah, it would. I think that's where your compromise is going to be. I showed the example for 60K and 120K. If your targets of interest are lower abundance, then you're going to have to decide whether or not you're going to be doing PRM or what type of scan speed you're going to be needing to tease them out from any type of background as well. It's a great question. And the Exploris, we should note, does have faster scanning than previous generations of Orbitrap. So I don't have the scan speed on there, but for 120K resolution, that's 2 hertz. And for 60K, that's 4 hertz.
Great, thank you. And another question related to Squad, but also the number of suites of mass spectrometers that Thermo offers. What are the features and or utility differences between IDX and IQX?
Oh, yeah.
And is Squad equally accessible with IDX?
Yeah. Short answer. Let me go back to my image on the IQX. Where is she? Okay, here's our IQX. Bear with me here. There are some differences, IDX and IQX. IDX has a front end that is has a cylindrical ion transfer tube, right? We also have that on the IQX. Then it has an S lens that is I don't know if you could see on the IDX, you then have an S lens here. On IQX, you have an ion funnel. Now, this is an ion funnel that was generated to be softer transmission so that you aren't really fragmenting the ions as they are being transferred into the mass spectrometer, right? So it is a gentle ion funnel, if you will. IQX also has, you can see this little bit here sticking out on the right. This is the auto-ready ion source. So what this is it's an incorporated inlet flex mix and its own emitter that goes directly into the ion funnel, which means that you can now schedule your calibrations and no longer have to stop your run. You can schedule it in the instrument control software to do your calibration. Additional differences on the IQX. This UVPD and 1M were not previously available on IDX. So now on the IQX, you have access to additional types of fragmentation incorporation in UVPD, and you have access to 1M resolution on the Orbitrap. Those are hardware differences. Then if we talk about Squad, is it accessible on IDX? Absolutely. You are looking at hardware differences that may impact sensitivity slightly. The ion funnel we've seen in some of the work is a little bit more sensitive than an IDX. And for Squad, I believe that's it, actually. Yeah, that's it. You're going to get a little bit more sensitivity on an IQX. Otherwise, you can still use the 2 detectors in parallel.
Great. And one of the last questions, it's more technical from a CD user in the virtual realm here. After running Compound Discover, if the MZ Cloud best match is low, around 60, for example, but the fish score, we didn't talk about.
I didn't talk about fish score.
If the fish score is high, like over 40, in your experience, what value should you consider?
Oh goodness, I don't know how to answer that because I don't use CD. However, Rahul or Bashar can either address it right now on the fly, or we will follow up on that to understand how to kind of bounce between the fish score number and the MZ Cloud match score.
If you would copy the questions.
I got it, yeah.
Okay. I wouldn't know to answer that either. Okay, from the room, other questions here? Well, Shen.
I want to ask, like, based on these results, why the isolation between quadruple and ion trap will be different depending on the thinking process of that?
Can you please repeat the question?
Yeah, when Elise was evaluating the Squad on the tribrid, we talked about different types of isolation, either ion trap or quadruple. I have to say at first, we hadn't considered this. From working with R&D and understanding how the ions are counted, which occurs in the ion trap, right? And how you can best parallelize the system and enhance your sensitivity, right? There is a difference in isolation when you are using a linear trap versus a quad. So I think that there is a more efficient isolation on the quadrupole versus the linear ion trap. I'm not sure I can answer why, but that was part of the consideration. And you need to, I don't even know. I don't remember the answer. That the end is going to be, Elise will have to tell you which became most efficient for her targets. But I think you do have to determine for your target which is going to be the most efficient.
About specificity, specifications, how is the scanning speed improvement in IQX or Orbitrap and other detectors?
Orbitrap's the same. On IQX versus what, IDX? Or
Explorers or?
same, it's the same Orbitrap. So it's the D20 Orbitrap, which is the only Orbitrap that we manufacture from now on. So on our cubes, our Exactive series instruments, any Exactive series instruments apart from the HF or the HFX has a D30 Orbitrap incorporated in it. You get twice as fast scanning speed on the D20. So it's a little smaller and there is a higher potential between the two electrodes. That higher potential allows you to scan faster and achieve the same resolution. So the smaller diameter does not impact the number of ions that you could put in there. So we are a trapping instrument company. So we have very well-defined incorporation of AGC control so that you do not get space charge, right? And that is not limited by the size of the Orbitrap. Decreasing the Orbitrap size increases the potential, which allows you to scan faster and achieve the same resolution. So on a D20 or anything that says HF in it or Explorers, you get twice as many scans, basically.
Uli?
In the real-time library search, so you mentioned in past slides that you can do HCD or CID instrument. Can you use the real-time library search to say if you didn't find a match in HCD, fragment it to the next get in CID?
I don't know. Is that a decision you can make?
You can have multiple decision.
Okay.
Multiple decisions.
So yeah, in the instrument control software on the Tribrid, because I'm recognizing that you guys have hybrids on the Tribrid, there's way more parameters and decisions you can make at any given time.
So you can also have, you can either, if it finds a match or if it doesn't find a match. So you can incorporate anything.
So I have lots of questions, of course, and that's okay, I guess. So UVPD. UVPD, we haven't talked much about it, unless you say you're so enthusiastic and it's fantastic. We had also speakers here about UVPD in former seminars, Jennifer Brockbelt and others. And what we found, or what is kind of a consensus, is that UVPD works fine or great when you have very intensive compounds, but it's because it's a fairly soft dissociation. You need to have quite intensive peaks and then look at the low abundant ions to kind of figure out what you are so excited about, double bond positions and so on. Is there a way to improve that?
Well, okay, so there's multiple answers for that, right? If we are to look at what Jenny Broadbelt does, she uses a different laser, right?
Yeah.
Which we understand. She did a lot of great groundwork for us to understand the fragmentation mechanisms of lipids using UVPD. So helpful when we are doing this work. I think there is a limitation. A limitation remains on the sensitivity of the fragmentation. And we have two detectors and we have MS to the N. These are areas in which we are improving that by doing multi-stage fragmentation. We can get more sensitivity in the UVPD. Also, we have work from Shen and work from Jenny. We know that adduct ions fragment more effectively in UVPD. This is an area that we could go into. If we talk to R&D, they want me to put lithium in every sample that we are doing UVPD in order to help improve the fragmentation. We don't necessarily want to do that or agree, right? But we are thinking of ways to improve that. You saw in AcquireX that you can use AcquireX and you can eliminate the adduct ion. You don't have to do that. You could keep that adduct ion or point it towards that. And then by using AcquireX and UVPD, you get deeper. So you're now no longer at the limit of kind of what you're saying by there being a sensitivity bottom. Now you have more time because you have AcquireX. AcquireX means you can inject more times, right? and you only need one scan. Orbitrap's beautiful, only need one scan. So you just have to hit it once at the right time, and you can inject more times to do it again for other low-level species. If you irradiate longer in the commercially available laser that we have on our instruments, you do improve the fragmentation a little bit more. So this is why it's nuanced. We have multi-stage fragmentation. We go after the adducted ion, not the protonated or deprotonated species, right? In order to get more effective fragmentation. And we use UVPD to really hit those low level compounds, or sorry, AcquireX to really hit those low level compounds. Again, come to Rob Wool's talk at ASMS Thursday. Don't know when, I think it's in the afternoon.
Not everybody can go.
Yeah, I know, but eventually we
so-
will have something else.
So have you considered EAD?
Yeah, so what I have looked at the EAD fragmentation that is publicly available from other vendors, and the fragmentation is the same, right? I will say I'm at a limit at what I can see because we don't have EAD in like our product portfolio. So when I'm looking at either publications or otherwise, I see that the fragmentation mechanisms are similar. I see that they have a significant sensitivity issue as well. Our push towards incorporating UVPD is to make sure that we can do it on an LC timescale and we can do it in a biological matrix. Otherwise, it's kind of useless in my view. So that is what we are presenting moving forward.
In the past, we have also like looked at positive mode and negative mode, and we found that sometimes negative mode is a bit, you know, less than optimal in terms of sensitivity in the instruments that we have here. Is there any reason for that?
I have no idea. Yeah, I don't know. Well, we can,
compared to like, you know.
the sources are different, right? Every instrument has a different source, and every instrument vendor has a secret sauce to make that work and to effectively transmit those ions from the source region to your detector.
Yeah, so overall, I think negative mode is a little underappreciated. You know, if you think also about Mass Frontier and whatnot, right?
Mm-hmm.
So there's so many, you know, focus on positive mode, but then, you know, we agree that negative mode has like fewer identifications and fewer peaks, fewer this, fewer that, and then, you know, sometimes I think like, is that because less attention was paid?
Probably.
You know,
Yeah.
or is it you know, just because, well, the interesting molecules all have the tendency to like protons or sodiums, whatnot, ammoniums, right? The further questions from anyone?
Question
Yes, Arpan.
online. I believe this is a squad related question. I'm making a little bit of an assumption here, but how can we utilize squad for plant extract secondary metabolites? I know you referenced the work Bashar did on tea, but maybe we could just kind of go over that again. And how is it different compared to the work that might be done on a top or a Q3?
Okay, I'll break that question down. How can you use squad on
Or
plant metabolite extract or secondary metabolites?
plant extract.
Secondary
or
metabolites. Yeah, so in the absence of standards, they're asking about, right? So if it's a secondary metabolite and you don't have something to create that calibration curve, how are you incorporating squad? Targeting them, it would be my answer on that, right? You can target these secondary metabolites that you know are there. If it's an unknown secondary metabolite, then it's real-time library search is how I would suggest utilizing a tribrid to do that. What was the second part?
And then how is that work different from, or how would that work be different from a top or a Q3?
A top or a triple quad. Triple quad fully targeted. So you are only seeing your secondary metabolites. No shame there. That could be what you're going after. On a top, I have to be honest, I don't use them. So on a top, I would go based off of lore, which is telling me that you need more than one fragmentation scan in order to get an appreciable MS2 spectrum. So even though what you are seeing in an Orbitrap, every scan is a spectrum that you can use, right? If you need to sum those, that means that regardless of how fast your detector is spec'd at, its operational speed is lower, right? You have different limits of detection and different dynamic range per quantitation on the two instruments. I could only speak to what we can find on an Orbitrap or on an ion trap. So I don't know what the difference would be. If we talk about SQUAD on an Exploris, your capabilities for polarity switching are not going to be there on a QTOF instrument.
Those are the questions online.
So let's continue with the quantitation. So, SQUAD is obviously targeted with the idea to do quantitations. And we just established, like if you have a standard, phenylalanine, 6 orders of magnitude is fantastic for this combination of accurate mass and ion trap based PRMs. That's really brilliant. But the point is that we need to be more quantitative, right? So there are different solutions. One solution is like, have completely labeled extracts and put them in, say, from yeast. That's a commercial solution from some company. And other people would say, well, put in 76 internal standards and use those as surrogates and hope for the best. So there are also people who say, oh, you know what, use machine learning and do magic. Machine learning always comes across as magic to me. And, we give you a model that predicts which compound would ionize how efficiently. And we can use that model and we give you molar concentrations. What is your perspective on these different approaches to quantitation?
Yeah, I mean, I'm of the opinion that I want to help you do your research more effectively. So I don't really have an opinion on which is best, right? I think they all fit, they all have a place in how you're doing it. The question that I think is that we are trying to address here is how do you build more quantitative accuracy in the absence of standards, like that question on secondary metabolites, right? How are you getting more precision and accuracy out of your data to know that you can make sense of your results? And what you're saying are all areas that we have also been considering. If you're using a C13 labeled yeast or E. coli, I mean, everything has a limitation. If you're trying to do machine learning and AI, I'm with you. It's magic. And also, I'm kind of starting to believe in magic. So I need to really learn a little bit more on what's happening there and how best to utilize it. There are limitations there. Whenever you build this type of machine learning algorithm, there are so many pieces that go into it. Your chromatography, your instrument, your resolution, everything, right? Buffer, yeah. Can you make the buffer the same, right? Like so many variables there. That's what scares me, because we understand that there are differences in capabilities of every laboratory. So if you don't take all of these potential areas for failure into account, then it's going to affect kind of what your quantitative accuracy is. And then how many standards can you incorporate? I mean, that's a debate that we can have, and it depends on your analyzer. It depends on if you like to do sample prep or not, right? It depends on how you are going to maximize your targets while not limiting your untargeted portion.
So we briefly talked about calibration curves, but one way to do a calibration curve is dilution sequence, right? Obviously, that's the simplest one. You could, maybe double the extract amount that you usually use or whatever, not too much because you go into saturation, but you can certainly dilute those as well. Would Compound Discoverer have that automatically included to say, well, this is my dilution curve, apply that to all my peaks, and just report on those that actually follow that type of dilution?
I have no idea. Do you guys?
Our mission yesterday, you always can have a script. So you can build your own model, including whatever equation you would like and apply it for the second one.
But it's not like automatically included.
Not in this way.
Yeah,
You can make
Yeah, in version 3.3, what you're asking for is not automatically included, just to repeat Bashar's answer. However, something I didn't mention with Compound Discover is you do have the capabilities to create your own nodes. And in Compound Discover, each node is a step in the data processing. So you can create a node to have it process your data and give an output based on your dilution.
So you also mentioned that you're skeptic about lithium or lithium fluoride.
About what?
Lithium or lithium fluoride as an additive to make certain lipids more shiny or other compounds. And from time to time, there are papers in organic chemistry that suggest that, and they say, that's the golden goose, that's the thing you want to do. And you were saying you're always skeptical about
Yeah,
it.
I
Why
did
are you
clear.
skeptical
That's a
about
good question, because it does help, right? So I'm not skeptical on the science or it being analytically necessary. I'm skeptical at incorporating that into daily global lipid characterization, or how many instruments do you have, right? I don't know what a constant addition of salt or will be doing to how frequently you're going to have to clean your system. I'm skeptical because we haven't tried it, right? So these are things that I consider. How robust is the solution? How can you implement it easily in a laboratory, right? And how can the user get the most out of it? And so these are areas that we consider when or if we will incorporate that into our solution for UVPD. Next year, I might be like, I'm a believer, totally into it. Yeah. So I don't know.
Very good to see this strategy and thinking. One reason why you would like to have a more sensitive instrument or kind of PRM capabilities is to go with lower amounts of sample.
Mhm.
So what is the concept for SAML to go towards single cell metabolomics or imaging, mass spectrometry and whatnot?
Yeah, I mean, Thermo, if you don't know, also does proteomics, right? So we do have capabilities to do low flow very well. And we have very good solutions for ion sources. Otherwise, to increase sensitivity, use lower amounts of sample. We have launched the Vanquish Neo, I believe last year. What's so cool about the Vanquish Neo is that it has a flow range without changing any kind of flow regulator or just without having to change any kind of flow regulator. The pumps go from 5 nanoliters up to 50 microliters, 100 microliters a minute, even better. 5 nanoliters to 100 microliters a minute. And in that range, you can do a lot of things. The limitation that we are finding is column chemistry and how small you can go in terms of column diameter, and having, like, you can do C18 clearly, right? Do that as low as you want. But if you do want different types of separation, then there are limitations there on what type of helicolumns you can get and otherwise. But it's something that we're working on, and because the community is asking for it. And so we are looking at increasing the sensitivity of our methods, maintaining robustness and data fidelity, utilizing the Vanquish Neo, easy spray columns, easy spray source. So, and getting the sensitivities as a teaser for single cell lipidomics. Rahul has data indicating that we can analyze the amount of lipid from a cell using easy spray columns on the Orbitrap Explorer 240.
Moshiro, do you have a question?
Oh yeah, so I just had a question. So now about squad, I think you just gave us a very comprehensive review of the software, pretty good. So I'm concerned about the sample preparation. So I remember last year I went to SMS, and I think Thermo had a introduction of the automatic sample preparation system.
Yeah,
So do you want
Accelerome.
to talk about that?
Yeah, Accelerome was created with proteomics in mind. So there are limitations to doing liquid extraction and other types of sample prep that is required for a small molecule. That's definitely a step we could go in to try and effectively use that sample handling robot for metabolomics. We just haven't done it yet.
Further questions online?
No questions online.
Okay, here in the room. Well, we stick around for the day. So please see Rahul and Bashar after the seminar if you have further questions that refer to details. Thank all three of you to come here to spend the day and yesterday. We know that it's a significant commitment. Also, we didn't even say so. Thank you for the effective collaboration, including at the Center for Excellence in Clinical Metabolomics in Sacramento. For those online who may not have heard it, we do have that collaboration in Sacramento going, where we do quite a number of demonstration studies together. So thank you everyone for coming here today. Thank you for the people online. And we will go for a summer break now.
Yes, we'll resume back in fall.
We will resume in fall. So be productive, go to ASMS, go to the hospitality suites and and the posters. And thank you everyone for being here.